we have an alkyl bromide, and we want to convert this. This was a little more challenging to an amide. That looks like this. Actually, that made too many steps. Let's just convert it to an amine. Or how about just this amide? Let's do this one first. So I have this alkyl bromide, and we want to convert it to this amide. And so when we're looking at this, we have the number of carbons. Yes, we've added a carbon. The functional group, also we made a change. Yes. So we've gone from this alkyl bromide, added one carbon, and then we've introduced this amide. So this one, I'll pause here for about 2 minutes to give you a chance to come up with a solution for this one. So I chose this one because it brings up a topic that is quite useful in these sorts of transformations. Because we added one carbon. So this carbon here of our amide that we've added. And if we're starting with something like an alkyl bromide, it seems like a good way to add that one carbon. There's two. One is we could use the nitrile like we were just seeing earlier, or this reaction with the Grignard reaction. So let's first convert this to a Grignard reagent, and then react this with carbon dioxide. And we saw that this will react with carbon dioxide. I'll draw the mechanism out for this step because this is the key one. So we ended up having this. And then we could go ahead and protonate this. So I'm going to show the arrow. Oops. And now we've... let's try the 5-membered ring again. I should stick with the 6-membered rings. This is a very useful transformation for two reasons. One here is we've added our carbon that we wanted to add, the Grignard reagent with carbon dioxide, so that's great. We now have the number of carbons that we want, but we're also left with the carboxylic acid. So that's good news because now there's all sorts of things we can do with this carboxylic acid. So let's turn this into the acyl chloride. And now with that acyl chloride, we can convert that to all of our other carboxylic acid derivatives. So if we wanted an amide, because this one happens to just be ammonia, choose excess. We're going to make our amide. Notice we cannot go from our carboxylic acid directly to the amide. If we were to take those species over here on the right, carboxylic acid, and react that with ammonia, shown here in NH3, it's just going to pick up that proton in an acid-base reaction. So that's why we're converting this into the acyl chloride and then converting this into the amide. Now, likewise, you could convert to the ester if you wanted as well. So the original reaction I had, other things here is we were going to do, what was I going to have us do? We were going to reduce this to an amine and then react with an anhydride, but we'll just leave it like that. So following in a similar pattern, this one's almost the same. If we have alkyl bromide and we want to turn this into an ester, something like this, can take a very similar approach. So we could first, I'll just use the same one here. Turn this into a Grignard reagent. We won't write out the whole reaction this time. React this with carbon dioxide. Generate our carboxylic acid. And then now we want to generate an ester. So we have here our carboxylic acid. We want this ester in the end. So there's a couple of ways you could do this. One is we can convert this. Let's do it the long way first. This is not how you normally would do it. You could convert this to the acyl chloride using thionyl chloride. I'm writing this like this hopefully for a reason. And then we would react this with an alcohol, say with pyridine again. And that would give us the ester that we want. However, that's the long way. It's taking 2 steps, so you have to work with this thionyl chloride. And so with the ester as our product, why not just do a Fischer esterification? So let's just treat this carboxylic acid with ethanol and some acid. And so they're in one step. We can form that product. So we're seeing now this connection between a lot of different types of reactions. We just had a couple selected ones here, very brief, that we can start to now introduce carboxylic acid, convert it to a carboxylic acid derivative, let's say, and then amongst those different interconversions can do a lot with synthesis. So Lorianne asks, amide hydrolysis under acidic conditions. So yes, I'm going to scroll up for a second. I'll come back to this one. Going up to the amide hydrolysis. This one here, amide hydrolysis, that was in the cyano group. This will end up making the carboxylic acid from the amide to get a carboxylic acid. For the carboxylic acid, I think I see what you're saying. You can't really go from a carboxylic acid to the amide directly because you're going to just deproteinate. So if you have, where was that? It's way up here, I think. Here with this carboxylic acid in the middle of the page, if you wanted to turn this into an amide, you cannot just take a nitrogen-containing compound and have it react with the carbonyl group because it's going to pull a proton off here. So instead what you need to do is to convert this into something else. So you can convert this either into an acyl chloride or an ester or even an anhydride and then take the amine and react it with this. So I'm not quite sure if I answered your question though. Okay, so I said I'd go back down to the synthesis. Well, let's try this here first in the last 2 minutes, all the way up here. Revisit this once again. So we've seen here, to recap this, a lot of these different carboxylic acid derivatives, and we saw that we have a leaving group of different sorts here on the left side, and that we can see that they differ in terms of their leaving group ability, which affects the stability of the compound. We can readily convert down the ladder, converting from the acyl chloride to each of these different groups. It's much more difficult to actually go back up. However, the few of the most important ones are the carboxylic acid can be made into an acyl chloride, or thionyl chloride. We can convert between esters. We can convert a carboxylic acid to an ester with the Fischer esterification. And our hydrolysis that we had today is we can take an amide and convert this to the carboxylic acid under the vigorous conditions. We described why we see these differences in reactivities with the different sorts of leaving groups and the resonance and leaving group stability effects. And then we went through a series of reactions of making each of these compounds and then carrying out interconversions amongst them. We noticed that in some particular cases, like with the esters, the reactions can occur under acidic or basic conditions, and it's important to keep track of the formal charges of the nucleophiles and electrophiles in those cases. Then today, now we also saw that the nitrile down here on the bottom shows similar reactivity rather than CO double bond, the carbonyl group. The cyano group, CN triple bond of the nitrile, shows similar reactivity. And then we just very quickly brought some of those ideas together for the synthesis, very, very briefly, as I mentioned. So that's going to do it, I think, for our discussion of these carboxylic acid derivatives. A lot of material to digest, I know, but hopefully seeing the similarities amongst the reactions and thinking about it from a mechanistic point of view, then you can see that there are these common themes. So then going forward next time, we'll get into different material and start thinking about what aromaticity means in organic chemistry, how to define